Welcome, everyone. Today, we're pleased to host Professor Amit Chopra for an invited talk titled Agentic AI Needs Interaction-Oriented Programming. Amit is a senior lecturer at Lancaster University in the UK. His core research focuses on software abstractions for engineering flexible, decentralized multi-agent systems, with protocols and norms playing a central role in that work. Amit's results have been published in major venues such as AAMAS, IJCAI, AAAI, and also the Web Conference. And in today's talk, Amit will reflect on the past, the present, and the future of multi-agent interactions, which is a topic of growing relevance to Agentic AI. So Amit, thanks again for joining us. And with that, please feel free to take over.
Thanks, Andre, for the introduction. So the talk is titled Agentic AI Needs Interaction-Oriented Programming. And I'll describe a little bit of interaction-oriented programming and where it intersects with Agentic AI and what the synthesis could be. So what is Agentic AI? It's the idea that we should exploit LLMs to not just have conversations with, to chat with, but to actually take actions in the real world, right? So, and there are lots of, so that's a really exciting thing, having LLMs do actions in the real world. So for example, an LLM could invoke web services, it could use some API, it could do database queries, and so on. And things like the Model Context Protocol, which most of you would have heard about, it promotes a standard way of describing, discovering, and using these tools. So that's where the MCP fits into this picture. So we can now, because the LLM is taking actions in the world, we can think of it as an LLM agent. So that's the basic idea of Agentic AI. And there are many variations to this idea, to this theme in different frameworks. A central sort of notion that has become associated with agentic AI is the notion of workflows. So here is what is a workflow? It's some organization of activities, describes some control flow between the activities. And here is don't try to read this picture, but this is from HL7. It describes a workflow for handling medical tests, involving laboratories and patients and specimen collection and so on. So it has several parties and they are doing various kinds of tasks. And this describes the control flow. So this is a UML diagram. But there are other notations like BPM, and most of you might have heard of, and formal, informal. So somehow it has become the central notion in agentic AI that what the system is doing is executing a workflow. So there are many frameworks with which you can start dabbling in this area of agentic AI and build systems. LangGraph is a famous one, a popular one. Autogen is another popular one from Microsoft. And what they enable doing is they enable programming multi-agent workflows. So in this setting, you can think of the agents. There are many LLM agents, and somehow there is an orchestration being conducted across these agents, and that's the multi-agent workflow. And so they give you abstractions for creating systems. Then there are frameworks like Airflow, which is described in a recent paper. Here, the idea is that you don't want to program the workflow. You want the LLM to generate the workflow based on the user's prompt, generate the workflow needed to solve the task. So if we see what's happening here, what people are trying to do is exploit LLMs to the hilt. So we don't want to program our systems anymore. What we want to be able to do is to chat, give an prompt to an LLM, which may then invoke other LLMs, which may generate those LLM agents as needed by the task and execute them, right? So the whole idea is to move away from programming, which is good, right? It reduces effort and generate the systems we need. And these are very dynamic. So for every task, you could potentially generate a custom multi-agent system. So no more programming, so you don't write workflows. Please, if you have any questions, feel free to ask them. And typically these LLM agents, the code that is generated by the LLM is in a programming language such as Python. The code that if people write code, if people program the workflow themselves, they're doing it in languages such as Python again. So you write functions and then describe an orchestration between those Python functions. Well, a stumbling block in this vision, I think, is that LLMs are unreliable, right? They hallucinate, they make incorrect decisions, give incorrect answers, and therefore, how can we rely upon them to take actions? Because the actions that are of consequence are often the social actions. They happen in a social technical system in the sense that there are other parties also who have an interest in the actions, and the actions have an impact upon them. So they have normative consequences, the action. So, for example, if you book a flight or something, then there is a commitment from the airline to provide you with a seat on that flight. Likewise, with hotel reservations, if you're buying something online, once you've made the payment, there's a commitment to deliver. So in general, actions have a normative effect. They may create discharge, violate commitments, have an effect on other kinds of norms, prohibitions, powers, and so on. They may affect trust in others. Uh, if an airline sells has only 100 seats on a flight, but ends up selling, the LLM agent ends up selling 1,000 seats on the flight. That'll be a big problem for the airline. In the minimum, trust in the airline will be will be affected. And actions, result in accountability. People may ask us to explain our actions. So can we rely on LLMs to take actions on behalf of its user? The goal is, if the goal is LLMs generate the multi-agent system or whatever system is needed to execute or to address the user's prompt, then can we rely on the LLMs to take those actions to do a good job? So you might have heard that ChatGPT via Operator, which is another OpenAI tool, it can now fill forms, but it actually requires the users to take the action. So, even they hesitate in automating everything because things can go wrong. So, the kind of multi-agent systems I've been considering are socio-technical systems, are in the socio-technical settings. There are many principals, autonomous principals, who could be people, who could be organizations, and they are aided in their interactions by their agents. So we can think the same way about LLM agents. They help the principals exercise autonomy. So here the agents are these uh, boxes over here in the center. And these agents are heterogeneous in construction. They encode the decision making of their respective principals. So it's the principal's agent, right? And they interact via arm's length communications by sending messages to each other. Nobody orchestrates anybody else. And no agent can generate other agent. They belong to different parties. So there is no possibility of doing that, right? So this is what I think of as a real multi-agent system. This is where the actions have real consequences. It's not like invoking tools to write some LaTeX, generate a PDF, but you're actually booking flights, you're making payments, and so on, actions for which you might be held accountable. And to address situations like this, although we haven't done it with LLM agents, but in general with agents, we have this approach called interaction-oriented programming. So the basic idea of IOP is you model a system, multi-agent system, in terms of interactions, and there can be various levels of modeling. You can model the norms, you can model the protocols, you compose and verify the models, and then once you have the model of the system, then each party can implement its own agents. to encode their own reasoning and so on. And what we've been driven by in the last 20, 25 years is that we want high-level abstractions that are closer to stakeholder intuitions. And we want to let the programmers focus on the business logic, not be sort of too not let the details of coordination, low-level coordination, take over their whole effort, but let them let them focus on whatever reasoning, business reasoning, the agent's principal wants it to execute. So in this sense, we want to empower both stakeholders and programmers. So I think there is an opportunity to synthesize agentic and IOP. I think of agentic. So, by the way, this is sort of joint. I should mention this is joint thinking with Murinder Singh, and we've been trying to move away from a centralized way of conceptualizing systems. So there isn't a central goal of the system that has to be executed or addressed. Each party has their own goals. So there is no workflow and so on. So current agentic is centralized. There is a task to be solved and the system is synthesized to address that task. Whereas IOP is decentralized. You have a model of the interactions, but what actually happens is up to the agents who are designed independently. Current agentic, so what I've highlighted in blue are, I think, the nice things about these paradigms. And current agentic, a nice thing about it is that it minimizes the knowledge engineering effort. You don't have to write explicit rules anymore. The LLM, based on common sense reasoning, its knowledge can figure out things unreliably, but it can. That's the main thing about LLMs, right? That they can reason in various contexts and come up with some solutions. So they reduce the knowledge engineering effort. And IOP also reduces the knowledge engineering effort, perhaps not currently not as much as LLMs, but because the abstractions are declarative, that it means that less effort is required in building the systems, in building the multi-agent system, in building agents to participate in that system, and so on. A problem with agentic is that they are unreliable. And I think IOP can help over there in that the models are formal. They capture interaction meaning. They capture the requirements that sort of motivate the system. And we can use those formal models to guide the agents in taking correct actions. So engineering is a science of the artificial. We all know that, it was articulated by Herb Simon in the 70s. And I think models are important because they precisely capture requirements of the engineering artifacts. I think we cannot leave all requirements to things like prompts and so on. They are imprecise, they're vague. And therefore, I think there's an opportunity to synthesize these two approaches. We bring models into agentic, not heavy, not low level, but high level declarative models. So let me tell you a little bit more about the kinds of things we've been doing in IOP. These will be familiar to some of you because we move around in the multi-agent systems community, but it'll be helpful for the others to know these things. So one of the things we do is we specify interaction protocols to model a multi-agent system. And an approach for doing that is information protocols. These are declarative protocols. A protocol is just a bag of other protocols. It's a composition of other protocols, and some of these protocols happen to be messages. So they're declarative. There's no control flow. There is no message ordering. You never say one in the sense that you don't specify, or rather message ordering falls out from more basic causality constructs. So I'll demonstrate what I mean by that. So here the protocol specifies the computation of a decentralized object via messages. And the messages contain information, obviously, and they convey meaning. And there are messages have keys which identify the enactments. Think of the keys as identifying the business transactions. You can have one protocol, you can have many enactments of it, each a different business transaction. And the causality adornments determine when a role may send a message in an enactment. So we constrain when a message may be sent by specifying the causality, but we never constrain when a message may be received. So it's fully asynchronous. A message may be received anytime, and it's fine. So here's an example of an information protocol. Suppose you want to specify an interaction protocol. The first thing you do is you think about the message meaning. So here's an example of an e-business protocol. You could have protocols for any domain, right? So information protocols is a domain agnostic language. It's like Python in a sense. You can specify a protocol in it for e-business or for auctions or for health or whatever domain of the application domain might be. So here's an e-business protocol. It has three roles: buyer, seller, and bank. And you're saying that the protocol computes an object consisting of ID, item, price, and status. So that's the parameters line over here. And it has a set of messages. It has these messages: offer, accept, instruct, and so on. The messages have have senders and receivers. So offer is a message from seller to buyer. So far so good, right? There's nothing novel here. And they have a schema, right? So offer contains ID, item, and price. And that's what gives meaning to the offer, right? The parameters sort of, in a sense, embody the basic meaning of the offer. That offer involves offering an item for some price. Accept means, there is an item, you accept some item for some price with some decision that you make. And it reflects the decision that you make. And if you tell the bank, buyer can tell the bank to make a payment to the seller. So that's the instruct message over here. And it contains the price which needs to be paid and some details about the instruction itself. So you think of just the meaning. So you specify, and all you've done is specify message schemas, nothing novel over here. But then you can think of the causality. So how are the messages ordered? Or what constraints do you want to place on when these messages may occur? So think of the messages like actions, because they're only sending, right? So you can think of them like actions. So when can a seller do an offer? When can a buyer do an accept? And the causality adornments capture that. I'll not go into the details too much, but out means, you can generate a binding for them by sending the message for the out parameters. They apply to the parameters, and in means you must know the binding from prior interactions. So in this protocol, for example, accept can happen anytime after offer. Why is that? Because once the seller sends an offer, it knows, because it produces the bindings for ID, item, and price, it knows these bindings, and accept needs the bindings to be known because they're all in an accept. That means the buyer can only send the accept after receiving the offer, which brings it the knowledge of ID, item, and price. So, but it's not saying that accept should happen immediately after offer, anytime after offer, because once you know something, you know it forever. So knowledge is monotonic in this framework. And so likewise, so this protocol captures that the requirements that accept, instruct, and shipment can happen anytime after offer. Transfer happens anytime after instruct, because instruct produces details, out details, whereas transfer has in details. And refund may happen anytime after transfer, because you want to say that, if you've received the money from the bank, then if the seller can't do a shipment, then it should do a refund. So refund can happen after transfer, but it's mutually exclusive with shipment. So you can capture a set of interesting constraints using causality, mutual exclusion, ordering, and so on. And what you're not doing is specifying message ordering. You're not saying, except like in a transition system, if you had a transition system which had, offer going into one state and from that state accept happening, it would mean that accept happens immediately after offer. So it doesn't have that kind of inflexibility. That's what causality buys us. It buys us very flexible protocols. And so this e-business protocol has 658 distinct enactment. Here's, and we have tooling with which you can verify protocols. This shows a snippet of the output of running verification on e-business protocol. We are telling it to print out all the paths of the protocol. And here it figures out one path is, seller sends offer, then it sends shipment. Well, why is the seller sending shipment after offer? Why is it not waiting for the payment? Or why is it not waiting for the buyer to accept at least? Well, maybe the seller trusts the buyer, and therefore, once it has made the offer and waited for a little while, it says, let me go ahead and send the shipment. Why not? So the protocols are very flexible. What actually happens in an enactment depends on the agents, but the protocol is not circumscribing the flexibility. Or here's another enactment. Seller sends offer, buyer receives offer, then buyer tells the bank, gives an instruction to the bank to pay. Then the buyer doesn't accept, and so on. So you can have very flexible enactments. So you can specify protocols, but you can also implement agents to enact those protocols. And this is where programming models come in. So this is joint work with Samuel Christie. So what we are doing is, you can think of an agent is sitting on a network. It's sending and receiving messages via the network. The agent has some custom reasoning. It's applying its business logic. For example, what does it want? If it's a seller's agent, what items does it want to offer? For what price? That is that particular agent's internal reasoning. There may be one agent who's interested in figs. There may be another agent who's interested in coffee and so on, is a seller of coffee and so on, right? What we pose here in between is a protocol adapter. And this protocol adapter is generic. It interprets the BSPL protocols. And what it does, it exposes an interface for the agent's reasoning, where it tells the agent, these are the actions you can take in this state. What do you want to do? So for example, if the seller has already sent an offer for figs for £5, in that state, there are two possible actions available to the seller. It can send another offer for whatever it wants. So it can start a new business transaction, or it can send a shipment in for the earlier sent offer. So it can send a shipment, but it has to bind the prior status, because the status is out in the shipment. So it can send the shipment. These are the available actions to it, but it has to do something. And so that is what the programmer writes. It writes this logic where it does something. So for example, the programmer writes a piece of code like this in Python. So Kiko, which is the framework I'm describing, is a Python framework. It says every day at 5 o'clock, check what the enabled messages are. So which are the possible messages it can send, and get the enabled shipment messages from them, and bind status to next day or whatever value it wants to. And that's it. The adapter will then go ahead and send the message. So it doesn't have to figure out, sort of encode the protocol logic, because the protocol logic is encapsulated in the adapter. So it makes programming very easy. And this is the power of declarative abstractions. Then we can also specify the higher level normative meaning for the actions in the protocol. So remember, the protocol had actions like offer, transfer, shipment, and so on. So you can, on top of that protocol, conceptually, sort of layered on top of the protocol, you can specify the meaning of those actions. So you can say offer com is a commitment from seller to buyer. It's created upon offer. And its meaning is that if offer happens, and then if transfer happens within 5 days of the offer happening, where the payment is greater than or equal to price, where the payment is an attribute in transfer, and that's greater than or equal to the price in the offer, then the seller is committed to doing shipment within 5 days of this transfer happening. So you can start specifying sort of the normative elements on top of the protocol. You specify the meaning of the protocol. You can have other commitments. Except com is a commitment that if shipment happens, then transfer will happen. This will be a commitment from the buyer to the seller, that if you ship, then I'll do the transfer. Then the transfer will happen. Refund com is a commitment that if offer com is violated, which would happen if shipment would not happen, then refund will be done. And transfer com is a commitment from the bank to the buyer that if it is instructed to do a transfer, it'll do it. Right? So you can specify the normative meaning. And then we have done work with Matteo Baldoni and Samuel Christie. Samuel Christie was the one who led the work on the Kiko programming model, the Python model I showed. Here we've implemented a logic programming style, logic programming based programming model in JSON, which is language for framework for programming agents, language for and framework for programming agents. This is joint work with Matteo Baldoni and Samuel. And here we generate a lot of code and so on in the back to support these predicates, these events. So these are events that are generated by our adapter. And the programmer can write pieces of business logic like this, that whenever the refund com commitment is detached, meaning that there was no shipment and therefore it's been violated, then the seller will send the refund. So you're a programmer who's encoding, who's implementing a seller agent, and this is your business logic. You're saying that if the commitment is violated, the offer com is violated, then send the refund. You could write other kinds of business logic. If some commitment is nearing violation, then you can send the shipment. So you can imagine the seller has some strategy by which it's discharging its commitments. And its strategy here happens to be that as it nears violation, it takes care of it, which is what we often do with many of our tasks. So IOP is very different from traditional ways of thinking about interactions, modeling, and implementing them. So I think of IOP as heliocentric, whereas the traditional approaches are geocentric. They have no consideration of meaning. Protocols are encoded as inflexible state machines or workflows, or mostly informally via UML interaction diagrams. In many industry settings where they try to standardize protocols, there'll be UML interaction diagrams or workflow-like notations that like the one I showed earlier, that'll describe the flow of interactions somehow, but there'll be an inordinate focus on message formats. There'll be like tons and tons of message formats. You need message formats, but I think the focus is mostly on that. They think that is the protocol. And programmers have to implement the interactions in very low-level code, handle all possible message orders. They make complex, and to avoid that, they make complex message delivery assumptions. So they'll assume FIFO delivery of messages or something like that, or even more complex, causal delivery and so on. And in general, there is no flexibility in these approaches. Basically, all the parties have to move in lockstep, whereas here in the kind of protocols I showed, there is concurrency. So for example, accept by the buyer can be concurrent with shipment from the seller. So nobody has to move in lockstep because they're moving in terms of, they're reasoning in terms of information. So a little bit about FIPA, ACL, and KQML because it came up on the forum. So I thought it might be good to discuss this. I think they're of historical importance only. They are inspired from Austin's speech acts, and there are a handful of act types, for example, inform. They differ a little bit between FIPA, ACL, and KQML, but they are of this nature: inform, promise, achieve, and so on. KQML is informal, intended for cooperative agents, which means closed settings. FIPA ACL semantics is in terms of mental states. So, for example, to promise something means speaker intends to do that thing. To assert something means speaker believes it. So they make assumptions about when a speech act, when a communicative act is valid based upon, and that requires knowing something about the agent's internal states. And they've been adopted in agent programming languages and frameworks. For example, JSON is inspired from KQML. Jade has support for FIPA, but they have some limitations. the types of communicative acts in practice are virtually unlimited. If you think about the protocol I showed earlier, all of these are communicative acts of offer, accept, instruct, transfer, shipment, refund. Uh, and so there is, so in other domains, there'll be other kinds of communicative acts. And there is no way to come up with a few, a small set of these and say, that's it, that introduces some distortions in then how we use them, because when you're limited to a few, but in practice they're unlimited, then we start bundling our variety into those few things, and it doesn't work out in terms of semantics and so on. And the other thing is that it's impossible because the agent's mental states are indeterminate to other agents. And even if we look inside the agents, we cannot tell what beliefs they have or intentions they have. So it's impossible to determine compliance in open systems. Open systems meaning where, socio-technical systems where the agents are contributed by different parties. So you can't determine whether they are behaving correctly, the agents. They're communicating correctly. So IOP fixes their limitations by emphasizing social agency. So like I said, every message in a protocol is a communicative act. So you're not limited. Whatever you want to specify in the protocol is fair game. And the social meaning of the messages is specified separately and modularly. So like we overlaid, the normative meaning here in terms of commitments on top of the protocol. And so that's how we capture meaning. And there is no reference to the mental states of agents. This is what we need to do if you're building open systems. And we cannot, sort of put them in, we cannot put references to mental states in the communication standards. An agent can always, think about what might be the mental state of the other agent and make decisions on that basis, but we can't put it in the communication standard. IOP supports decentralized operations, which was not a focus of these earlier approaches. And it's a better, more faithful realization of Austin's ideas. So IOP is also inspired from Austin's ideas. His idea was basically that when we speak, we are actually taking actions and we are changing things in the world. So IOP is more better, is a better faithful realization because it takes the social stance that we are changing the social state of the world somehow. So I think it's time for new agent communication standards based on IOP. We have lots of running code. We just need rough consensus echoing IETF's mantra. That if you want to standardize something, first build it, and that'll be the basis for standardization. And we built lots of stuff. And here, stuff is available in this repository over here in GitLab, gitlab.com/Mazur. So coming back to agentic, what could be some directions worth exploring? So again, this is with respect to IOP. And we can think about two main directions. Can LLMs help us design multi-agent systems in the sense of design specifying protocols and norms? Because they have a lot of knowledge. They're trained on the World Wide Web and all kinds of data sets. And so they might have a notion of what are the norms applicable in certain situations, what are the kinds of messages that need to be sent in certain situations. So could we exploit that knowledge to design more robust, more how do you say it, more complete set of norms and protocols for a multi-agent system. And in this, I think we should exploit the verification tools that we have developed. So when an LLM comes up with a protocol, for example, we can run the verification tool on it to verify whether it's safe, whether it has some other property. We can develop some verification methods for norms and use that to feed back to the LLM. And perhaps LLMs could do it themselves. One LLM produces the protocols, another runs the verifier, comes up with the properties maybe from natural language descriptions and runs the verifier on it and feeds the result back to the former LLM, the first LLM that came up with the protocol. So various configurations worth exploring. And the other direction, sort of the big direction, is can we exploit LLMs to enact multi-agent systems? It's to sort of make it so we have LLM agents. So the LLM is the heart of the agent, but it exploits our protocol and norms-based frameworks like the ones I showed earlier, those programming models to make decisions. So it's not completely unstructured, completely free from, but it's guided by the adapters we have developed. So two basic things: designing multi-agent systems and enacting them, making it the reasoning engine and at the heart of the agent. And there may be several others. I've just started thinking about these things in the last few months, but there may be others. So I want to end with this slide on the synthesis, to sort of emphasize where I think the synthesis lies. The bad things about current agentic is that they are workflow oriented, centralized. The good thing is they reduce significantly the knowledge engineering effort. I think they're going too far where they want everything generated from prompts. I think what we should do is exploit models as well so that we bring some quality to the engineering effort. And this is where IOP can help. And that's my last slide. Thanks for listening.